There are 9 class periods left plus the final exam. We can do this for 9 more class periods, right? It sounds better than 3 weeks. We can do this for 9 more class periods. So homework, again, for the 2 of you who have not quite turned it in yet, homework is due at noon from chapter 8. The next homework assignment from chapter 9, which is just the one section, we only spent 1 day on chapter 9, we're going to spend 2 days on chapter 10, is due next Monday, April 27th. And again, all of these are in the document on Moodle with the revised course schedule. All of the assignments are also set up on Moodle with due dates, so you can see when they're all due. That was the first thing. Second thing, proof notebook. So remember, we decided last day of class, which is May 8th. And you can submit it on Moodle, or if you are super proud of your handwritten whatever and you want to mail it to me, let me know and we will make arrangements for that also. We can do it either way, whatever works for you. Those are my introductory whatevers. I think I'm going to hold off on homework questions on chapter 9 until Wednesday, if there are any, because I'm assuming that you are finishing up your homework for chapter 8 for today. But anything else for other questions before we get going in chapter 10? Anybody, anything? Content, procedural, schedule, anything. Anything before we get going? No, we're all good? Okay, all right. Today then is math that is going to take you through the rest of your mathematical career. It is used all the time. And it's gonna be today and it's gonna be Wednesday. And we're gonna do some examples. And we are now back to very highly structured proofs, okay? So today and Wednesday, very, very highly structured proofs. I'm gonna call this section 10.0 because it's kind of the introduction. This is one place where the book is just arranged a little bit weird and I don't love it. I don't know why he didn't make it 10.1, but whatever. So section 10.1 is mathematical induction. Can tell I'm Monday out of practice. My handwriting is deteriorating from not having done this over the weekend. All right, mathematical induction. So this gets used when you have a statement to prove for a list of numbers that has 2 requirements. So this list of numbers has to have 2 requirements. First of all, the list has a smallest number. So that's the first one. There has to be a smallest number in the list. Your list has to have a smallest number. And secondly, and this isn't going to mean anything to you right now, but I want to say it anyway, just because it's mathematically precise. The numbers in the list can be ordered or can be placed in order. Again, you don't have enough background to understand what this means. And even after taking a real analysis class, if you do a math major at WLC, you'll kind of have an understanding of what this means. Because right now you're thinking, okay, how can numbers possibly not be ordered, right? 1 is always smaller than 2, 3 is always smaller than 6, 7 is always smaller than 1500, right? Numbers can always be ordered. If you talk about the real numbers, so remember that both rational and irrational numbers, you can't order the real numbers. You can't place them in order. There is no inherent ordering system on them. And Dr. Brown is way better at this than I am because this is an analysis idea and she is an analyst. There's 2 big branches of math. One is analysis and one is algebra. She's an analyst, I am an algebraist. And in algebra, we really don't care about ordering numbers. So this is not something that I am super familiar with. I can talk about it kind of, sort of, basically, but she's way better at it. So the point is, and I understand that you don't get this and that's okay. I just want to say it to be mathematically precise. Sometimes there are sets of numbers that you can't order. and therefore you can't use induction on those. So yes, sets that you can use induction on would be the positive integers. That's going to be the most common one that we're working with. You could also do the natural numbers, which is actually the same as the positive integers. You could do the whole numbers if you wanted to. Remember that the whole number starts at 0 instead of starting at 1. So you could do the whole numbers, that's okay. The smallest number doesn't have to be positive. A lot of times it is, but it can be negative. As long as there's a smallest number, that's fine. You can, I think, I'm gonna put this down with a question mark. I think that you can do this on the rational numbers. I'm pretty sure, yeah, there's an inherent ordering in the rational numbers, so I think that you could do this on fractions also if you wanted to. You have to think about how to order fractions, and this is a really cool proof, which I won't do today, but you can. No would be, oh sorry, and I need to say positive fractions. We can't say just rational numbers, we gotta go with positive. No, and this is what I asked you in the reading assignment, is the integers in general, because there's no smallest integer, right? And a couple of you answered that yes, you could, but you'd have to do an induction proof in 2 directions. Technically, that's true. You'd have to put it together in 2 halves and say, my smallest number is 1, and I'm going to go forward. My smallest number is 0, and I'm going to go backwards. So yes, kind of, but not a regular normal induction proof. Same thing would apply for the rational numbers because there's no smallest rational number. And then the positive real numbers, or the real numbers in general, but the positive real numbers you cannot do an induction proof on. There is a smallest positive real number, but you can't order them. It doesn't work, so you can't use induction. The set that we are mostly going to be working with is the positive integers. So almost always our induction proofs are going to be on the positive integers, but it doesn't have to be. You can do whatever you want. Okay, 2 steps in an induction proof. And again, I asked you this in the reading assignment and you did a good job of explaining them. I want to make sure that you have the terminology. So the first step is always called the base case. That's my first step, base case. And this is prove the statement is true for the smallest number. So you got to prove that the statement is true for whatever the smallest number is that you're working on. That's step number 1. Prove that the statement is true for the smallest number in your set. Secondly is what's called the induction step. So that's our second step, base case and induction step. The induction step is a conditional statement, so it's an if-then. That means we get to assume something and we need to prove something. So we're going to assume the statement is true for statement is true for K, and this is called our induction hypothesis. We're assuming it, so it's going to be a hypothesis. All right, so this is our induction hypothesis. Assume the statement is true for K and prove the statement is true for K plus 1. Okay, so that's our induction step. It's an if-then. If the statement is true for K, then the statement is true for K plus 1. So we get to assume our if, assume that the statement is true for K, and prove that the statement is true for K plus 1. If I were actually in the same room with you, what we would do now at this point in time is I would bring my dominoes in, and I don't have them at home. They're in my office, so I can't even show you them on my camera. But I would bring my dominoes in and say, okay, we're going to line up a line of dominoes, and the goal is to knock over all of them. So we have to do 2 things. We have to show that we can knock over the first domino. That's our base case. And then we have to show that if we knock over any domino in the list, the kth domino, then the next one is also going to fall over. K plus 1 is going to fall over. If we can show these two things, then we can show that we can knock over all of the dominoes. And normally dominoes would be knocked over on the table in front and it would be fun. And I am sorry that you are not getting that experience today, but we'll do it sometime in person. That's the basic idea. All right. So induction is those two things. It always has a base case and it always has an induction step. And your induction step always has two parts also. What do you get to assume? What are you trying to prove? Are we good on the basics before we try some examples? Everybody good? Okay, all right. Goal today is to get through, I hope, through 3 examples. So, for example, here's my first one. Prove for all n living in the positive integers that 1 plus 2 plus 3 plus a bunch of dots plus n is equal to n times n plus 1 over 2. For all n living in the positive integers, we want to prove that 1 plus 2 plus 3 plus a bunch of dots plus n is equal to n times n plus 1 over 2. This is my statement that I'm trying to prove. So because of the for all n living in the positive integers, that tells me that I want to do induction. And I usually am going to label these. So we'll say proof by induction, just so that the reader knows what exactly proof technique we are using. So we are using by induction. Induction is our proof technique. I want to label. So here's my base case, first of all. I totally want to label the 2 parts in my induction proof. So we want to label the base case and we want to label the induction step. So for my base case, I'm going to write this in words once, and then in the next one, I probably won't write this first one. So I need to show the statement is true for n equals 1, right? I'm working with n in the positive integers. 1 is my smallest positive integer, so I need to show that the statement is true for n equals 1. This statement, this first sentence, you don't have to write down again if you don't want to, but we're doing it just the first time. So this I can turn into an equation. On the left-hand side, if n is equal to 1, I just have the first piece, right? So I just have 1. On the right-hand side, I need to plug 1 in. So I need to show that 1 is equal to 1 times 1 plus 1 over 2. I'm plugging in n equals 1. When I plug in n equals 1 on the left side, I just get one thing that I'm adding up. On the right side, I get that. This is easy. We can say this is clear. No problem. Sometimes if the equation is a little more complicated, I might ask you to start on one side and work your way to the other side, but this one is super, super easy. 1 is obviously equal to 1 times 1 plus 1 over 2. Easy. Good? Base case? All good? Good there? Give me a thumbs up. Yes, nodding. Yes, good. Okay. All right. Induction steps. So once again, I am labeling the parts of my proof, and so I am going to label my induction step. So we want to assume the statement is true for K. Assume that the statement is true for K. And I need to show the statement is true for K plus 1. So I'm assuming that the statement is true for K, and I need to show that the statement is true for K plus 1. Again, next time, probably not going to write this one down. We'll jump right to an assume equation and a need to show equation. But in this first example, I want to show you where this is coming from. So my assume is going to be, I get to assume that 1 plus 2 plus 3 plus a bunch of dots plus K equals K times K plus 1 over 2. That's my assume, right? I am assuming that the statement is true for K. So I need to plug in K into my statement up above. That's my assume. And then I can also come up with the need to show equation. So we need to show 1 plus 2 plus 3 plus a bunch of dots. I'm gonna write plus k and then also plus k plus 1. It's gonna be easier in the next step if we put the previous one of k and then put my next one of k plus 1. So that's the left side, and I need to show that that equals k plus 1 times k plus 1 plus 1 over 2. Trying to show that this statement is true for k plus 1. So wherever I see an n, I'm putting a k plus 1 instead. And I'm just keeping one previous term on the left-hand side and keeping it instead of putting it back into the dot, dot, dot. It's gonna help us out in just a minute. Are we good with our assume and what I need to show? Everybody's good there? Happy, yes? Okay, so if I were in class, I would have you answer the question. My very favorite question to ask, left side or right side of the equation? Left side or right side of the equation? Oh, let's do fingers. Left side or right side? What do we want? Left side is 1, right side is 2. You want to start on the left side or the right side of the need to show equation? 1 or 2? Left side or right side? What do we got? Fingers. You gotta give me something. We're having lots of people say 1 and people aren't voting. All right, we'll leave the people who aren't voting. Goodness. Left side. Let's try to start on the left side. So this is my equation. This is my, we know that. Left side, 1 plus 2 plus 3 plus a bunch of dots plus k plus 1. That's my left side. Eventually I have to get to k plus 1 times k plus 1 over 2. This is where I'm trying to get. So here's why I kept that k. The first pieces I can replace according to my induction hypothesis, right? Go back and look at your induction hypothesis. We know what 1 plus 2 plus 3 plus a bunch of dots plus k is equal to. This is k times k plus 1 over 2. That's from my induction hypothesis. And then I still have plus this k plus 1 out at the end. So the part with the curly bracket underneath it is from my induction hypothesis, and then I still have this k plus 1 hanging out at the end. All right. My right-hand side only has one piece, so it would probably be a good idea to try to get only one piece on the right-hand side now. So let's do a common denominator of 2. So we're gonna get k times k plus 1 plus 2 times k plus 1. Common denominator. K times k plus 1 plus 2 times k plus 1. And at this point, you have choices. You can do this however you want. You can either multiply out, or you can recognize that these two pieces have a common factor. So if you want to multiply out and then FOIL, you can absolutely do that. I'm going to show you a slightly different way to do it because I don't think you would necessarily think of this one, but sometimes it's a little bit easier. So both these pieces have a k plus 1, right? I can pull that out. We've got a k plus 1. In the first piece, what I have left over is a k. And in the second piece, what I have left over is a 2. And then this is all still divided by 2. So in that first piece, if I pull out a k plus 1, I have a k left. In the second piece, if I pull out a k plus 1, I have a 2 left. And now we are right there, basically. So this is when you got to go back and look at what your right-hand side was supposed to be. I was supposed to have a k plus 1. We've got that. That's fantastic. I was supposed to have a k plus 1 plus 1. I have that. I just have to rewrite it to make it look like what it looks like, and then divided by 2. So I can totally rewrite this to make it look like my desired right-hand side. K plus 1 plus 1 over 2. That's good. That's what I wanted. Actually, I don't earn a smiley face quite there yet because I haven't written my therefore statement. We'll erase that smiley face. You don't have to rewrite the whole statement again for a proof by induction. You can just say, therefore, the statement is true as desired. You don't have to rewrite it. So therefore, the statement is true as desired. And then we've earned our smiley face. Okay, quick recap before we do another one. Here we go. So base case, showing that the statement was true for whatever the smallest value of n is, and you got to be careful of what your smallest value of n is. Induction step, assuming that the statement is true for k, and then showing, my need to show is that it's true for k plus 1. And my need to show almost always gives me an equation, and we know how to deal with equations. Start on one side, work your way to the other side. I'm going to stop sharing my screen for a minute so that we can see if we have any questions at this point.